This video is the fourth and final video for Chapter 4 for the unit on equilibrium for Physics 12. It's our second day looking at equilibrium on a beam, where we're going to use two conditions for equilibrium. And the only difference today is when we go to take a look at calculating torques. Down there in purple I have that torque calculation where it's the R, the lever arm, the F, and then the sine of the angle. Last day, all of the angles were 90 degrees, and now we're going to find that some of them might not be 90 degrees anymore. And we're just going to do three examples. Here's the first. It's in your note booklet. It's got this beam. Looks like the whole beam is 5 meters long from one end to the other. And on the left there, I see the beam is 16 kilograms. So the entire thing is 16 kilograms, and you can pretend that all of that mass is acting directly in the center, 2.5 meters in from either edge. There is a cable that's pulling it up. It looks like it's up against a building over here, maybe on the left. There's like a shelf sticking out, cables holding it, and then there's this interesting package, 24 kilograms, with its center positioned 0.5 meter in from the edge of the beam. And the request is that we find the force of tension in the cable and the components, the X and Y components for the force from the wall back here, where that blue beam meets the wall. All right, well, I need a free body diagram. I'm going to put on every force I can think of there. I've got a couple of mg's. One is from the blue beam itself. That would act right in the middle of that 5 meter long beam, 2.5 meters from either edge. There's the mg from the 24 kilogram package. Now, this next force from the cable, I have a choice. I can write it as two forces, like a tx and a ty, or I can show a diagonal force with an angle. Either way uses two numbers to get there. But I already know the angle is 25, so I might as well use that information, and then I only have one unknown, the actual diagonal. Back at the wall, I don't really know what's going on here. The wall could be pushing left and right and up and down. I can show that as a diagonal with an angle, or I can just show it with components, with X and Y components. You and I have that choice. We can show it either way. They did ask for the components of that force, so I'm thinking that it might be just easiest if we show it as an X and a Y force. But there's nothing technically wrong with drawing in a diagonal force with an angle. Either way is fine. It's just that sometimes the algebra works a little bit nicer for one than the other, so be open-minded. That's everything for this story. It is totally possible that the 24 kilograms is so large that it might be creating a little seesaw, like a little tip here, a little teeter-totter, and the blue beam's end on the left may actually tend to go up. We may end up with an F force from the wall in the Y direction that's actually down, but the math will tell us in the end if we need that. So now I want to try to find those missing things, force from the wall in the X and the Y, and the tension. I'm going to start off balancing forces in both the X and the Y direction. There are so many forces, we have to do them separately in components. So looking back at the picture, what forces are in the Y direction? Well, clearly this one is up, the mg's are down, and a portion, not all, but a portion of the tension is also up. And so in the Y direction, I could write this. All of the force from the wall in the Y direction, which right now I'm assuming is up, a portion, a component of that diagonal tension is up, and then the mg's are down. And I boil that down as much as I can, and I get to here. It is a true statement, but there's not much more I can do with it at that point. It's just got two unknowns to it. Okay, well, looking back in the picture, let's go back. Let's look at the X direction, left and right. I've got this force that's actually going to the right. It's happening over on the left end of the story, but it's to the right. And then there's a chunk, a portion of the tension that's actually going back left. And so balancing forces left and right, I could say, oh, okay, that force from the wall in the X direction, it's a right-going force, balances out with that tension, but only a portion, that T cos 25. Another equation with two unknowns, and not even the same two unknowns. There's now a third unknown here. So we need something else. We're going to have to go with some torques. And so we want to go to that picture and think about a good place to go and put a pivot. My thought, if we put a pivot over at that left side of the beam, not because it's the end of the beam, but because if I put a pivot there, I get to ignore two forces for the price of one pivot. That's where I'm going to do that. So I'm going to go and pivot right at the wall. And if I pivot there, I don't even have to worry about those two forces for a brief period of time. And I want to get that torque that adds up counterclockwise, balancing out with the torque that goes clockwise. Okay, so let's go look at the picture here again for a second. Counterclockwise, if you're pivoting at that left side, Counterclockwise would come from the tension. A portion of that tension is perpendicular, so we can just ask the torque calculation to do it, the RF sine of the angle. That's going to create a counterclockwise twist. And the two MGs, with their 90-degree angles, those are going to create some clockwise twists. And so we're going to end up with this. Yes, it looks a little long, but it's the same cadence every time. You have an R, 3 meters out to the cable, an F, and then a sine of an angle for how that tension meets the beam. And then again, an R, and then an F, and I was too lazy and didn't have enough room to write it in, but right here would be sine of 90. And then an R, and then an F, and then again, a sine of 90 right there at the edge. This equation, although it's long, it's not quadratic or anything, it's just nice and linear, and you can solve it, and you can see that the tension needs to be 1,140-ish newtons. Now we can go back, do a little substitution back in here, and this whole story is done very fast. So substituting, I can go and figure out the force from the wall in the y direction. Turns out it's actually down, right? We were suspicious that maybe that would happen. The math has said, no, indeed, it's 91 newtons down. And then substituting into the other equation, looks like the force from the wall in the x direction is 1,036 newtons. So we can tidy those up with our sig figs, 2 or 3 sig figs, and we've got the answer there for this problem. So we're using both conditions of equilibrium. We actually had some good success starting with the second condition because we could ignore a couple of forces by carefully placing our pivot. So especially if you see 2 forces acting in one spot, that's always a great place to put the pivot. Okay, just 2 more examples to go. Each one's kind of got a little interesting story to it. This one here, got this diagonal pole holding up a streetlight out over an intersection, kind of cantilevered out like that with a cable, a horizontal cable that goes from C to D. And they're asking you to do really nothing but find the tension in that cable, right? That cable that goes from C to D. So what I want to do is take this picture and turn it into a free body diagram. Think about all the different forces that are acting. And here are the ones that I could think of. There were some MGs. And if you imagine drawing in a vertical line right from this point D going straight down, it makes a corner with this 42-degree angle. And so a straight down line here, like these MGs, they have to meet at a 48-degree angle in order to make that 90 degrees on the corner. So I've got those 2 forces going in there. There's also the force from the cable. It's 42 degrees for the angle, and I don't know its size. In fact, I'm looking for it. The whole goal is to try to find this tension. And then there are, again, 2 forces down here at the bottom. You could draw it as a diagonal force with an angle. You don't know either the size or the angle, or you can just draw it as an FWX and an FWY. Options. You can draw it either way. I'm just choosing to draw it this way. Now, here's what I'm finding. You can balance forces up and down and left and right, but usually you get stuck right away. So it might be interesting to try jumping right into working with torques. We just have to put a pivot in a nice spot. And I'm going to put my pivot right there. Not because it's the end of the beam, but because there are 2 forces there and I won't have to worry about them twisting the beam. The only forces that can twist it are the 2 MGs, which in this picture look like they will twist clockwise, and the tension, which looks like it'll twist counterclockwise. And when I go to write these torques down, I just have to think of R's and F's and sines of angles. Now, this question has a point. There's something kind of neat about it. This MG, it's the actual pole, which has a mass of 50 kilograms. It'll be an MG located right in the middle of the pole. It's 5 meters long, so it's 2.5 meters away from the pivot. That's nice. That's easy. The other MG is the streetlight. It's at the far end of the pole, 5 meters away. But this tension, it's not totally clear how far it is from A to D in this picture. And at first glance, you might think, oh, I've got to go and grab my calculator, do a little SOHCAHTOA, as they say, and figure out that A to D distance. And you can. And I want to show you that that is an option, right? So you could say, oh, I'm going to balance my torques counterclockwise with clockwise. And when I do, I have this mysterious value that I have to go searching for, right? So that's that value up in here from A to D, from where the pivot is to where the force is acting. So you could do that, and you could find this number with just a little trig calculation, and it ends up being 4.78. It's actually an irrational number. It's just got a lot of decimals to it. Infinite number of decimals. Well, what's interesting is when you take that number on your calculator's display and multiply it by the sine of 42, it turns out it's exactly 3.2. And so what just happened here, and this is kind of the point of this example, is that 3.2, it goes back to that day when we were talking about how you can deal with forces that are not at 90 degrees. And we said, well, you could resolve the lever arm. That's the phrase, to break up the lever arm, break up the wrench. And that's really what we just did. We can look at it and say, yeah, A to D is that 4.78 distance. But if you ask yourself how much of that distance is perpendicular to the cable, the answer is right here, 3.2. So next time if we see it, we can save a little bit of time. And if you don't see it, you've really only lost about 10 seconds. It's not a big deal. Now solving, it's actually pretty easy. Even though these things look really long, they're really just R's and F's, right? R's, F, and then the sign of the angle, and the R, and then the F, and then the sign of the angle. And it solves really fast, and you can see that the answer is 1,420 newtons. Now, an interesting little side question here. What if this question had asked you to find out how big the horizontal wall force is? Well, let's just go back and look. You know, if you were asked to figure out how big force wall in the x direction is, well, if you balance left and right forces, it's the only thing that can balance out with this tension. So we've already figured out the answer. It's the answer we just found, right? It's the answer for the tension. But here's my point with that. What if I didn't ask you to find the tension? What if I said, hey, go find the horizontal wall force? I would actually not find the horizontal wall force. I would go and find the tension. I would still pivot here and ignore the horizontal wall force, because it's nice to pivot at that spot and ignore two forces. Once you know the tension, then you can easily answer this question of how big the horizontal wall force is, right? It's just going to be 1,420 newtons based on that picture. So sometimes you find something else first because it's actually easier. Final one, little story about a person climbing a ladder. So this person, they're going to be 80 kilograms, and they're actually going to move up the ladder to different spots on the ladder. And so we're going to try this question out twice. Once when they're 1.2 meters from the corner, and once when they're 3.2 meters from the corner. We want to make sure this ladder doesn't slide out, that the heel, or sometimes called the butt of the ladder, doesn't slide out to the right. This is a coefficient of static friction for that floor, and I want this to be like a wall of ice. It turns out if there is friction up here, the problem becomes incredibly challenging to do. Sometimes it's not even doable. So we'll pretend there's no friction here, only like a straight out normal force from the wall. Down on the floor, there could be a normal force and a friction force. The ladder is 16 kilograms. It's 4 meters long. But again, that person is going to move to a few different spots on the ladder. So free body diagram for a ladder. We've got the mg of the ladder material itself. I'll just make that a small m right in the middle of the 4 meters. And then there's the mg for the person on the ladder. And that's going to move. One time it'll be 1.2 meters, and then the next time 3.2 meters from the pivot, from the heel of the ladder. Down at the floor, got a friction force that's holding the ladder in because it's tending to slide out, and a normal force. And then up at that frictionless wall, there's this force out from the wall. And we'll just say that there is no friction there. So just looking at balancing forces left and right, looks like this force balances with that one. Balancing ups and downs, that normal force from the floor balances out with the mg's. And then there's the issue of the torques. When it's time to deal with torques, let's pivot here. Not because it's the end of the stick, but because there are two forces there, and it'll be really nice. Okay, so let's run through what we know. Balancing forces up and down, that normal force from the floor has to equal the weights down. Those are the only ups and downs in the story. We now already know how big the normal force is, 941 newtons. Now that you know the normal force, let's go and find, and let's be super careful how we word this, the maximum possible friction force. I'm not saying this is the friction force. I'm just saying this is the maximum it could be based on this normal force of 940. Because with static friction, when you go mu times Fn, you're actually figuring out warning values. So warning, please don't ask for more than 376 newtons of friction. You can have any number you want less than that, but you can't get more than that. Now, balancing torques. Looking back at that picture, torques counterclockwise would be because of the mg's, and the torques clockwise, but there's only one, and it's from that wall all the way at the end of the stick. And so we have this. 2 meters to the middle of the stick, middle of the ladder. Here's the force of the ladder itself, and that force of gravity meets the ladder at 30 degrees. Here's the person, there's their force, and this is how far they are from the pivot. They're going to move around. We do this twice in this question. And then here's how their weight meets the ladder. It meets at a 30-degree angle. Okay, I'm just going to go back and look at that 30-degree angle. We're told there's a 60-degree angle when things that are horizontal meet with the ladder. So that means things that are vertical will meet with the ladder with a 30-degree angle. That's where I got the 30 from. So the angle tucked in here between the MG and the blue stick, that's going to be a 30-degree angle. Okay, so I have this, and then this is the force from the wall, 4 meters away with a 60-degree angle. Now we do actually know the value for x. In fact, there are 2 different values for x. So you would do this story twice. It's got like a part A and a part B to it. In part A, when you put that value in for how far the person is up the ladder in here, you'll find that this value, the force from that wall, needs to be 181. It's a big, strong wall. I'm sure it can do it. In part B, when the person's that far up the ladder, now the wall pushes with 407. Again, it's a big, strong wall. I'm sure it'll be fine. I'm sure it can do it. But now let's think about the ladder's bottom, that heel of the ladder, where you're balancing left and right forces. We know that the friction force down at the bottom of the ladder, its job is to balance out that force from the wall. Okay, let me go back and look at the picture again. Whenever the wall starts shoving to the right, it's going to be up to friction to pull the ladder back left. And if it doesn't, then the ladder is going to slide out. So how well is this going to work if those two are supposed to be the same? Well, in part A, the force of friction would only need to be 181. Now I know we did a calculation a second ago and looked at friction to be 376, but that was just a warning. The actual value for friction will be 181, and that's under the 376, so you're fine. But in part B, you would be asking for 407 newtons of friction, and you're not going to get it because you only get 376. So this ladder will not hold when that person is that far up the ladder. They will be safe for a while, but then they'll climb to a point where that friction force is going to be right at its 376. That'll be when the wall force is 376. And at that point, the ladder will slide out. So it's very dangerous. That's why you want to have somebody hold the ladder whenever you go up. And that's the end. So the key thing today, I'm going to go way back in the notes. The real key thing today was how when you've got forces that are meeting the beam at an angle that's not 90, like this first one here, this tension, you have to remember to go R times F times the sine of the angle, right? The sine of the 25 in this case. And that's the end of the chapter.